Dear student, warm welcome to NPTEL Phase 2 video course on Geosynthetics Engineering in Theory and Practice. My name is Professor J. N. Mandal, Department of Civil Engineering, Indian Institute of Technology, Bombay, Mumbai, India. The name of the course, Geosynthetics Engineering in Theory and Practice. This is Module 6, lecture number 31, Geosynthetics for Reinforced Soil Retaining Wall. Now, I will show recap of the previous lecture, check for the seismic loading, design a precast segmental block retaining wall of height 8 meter with the geogrid as reinforcement, and one example stress due to wheel 1 and 2, and now we will continue with the other wheel. Now we have shown you this earlier that this is the wall, this is precast concrete block, this is the leveling part, and here is the number of the layer of the geogrid reinforcement we have already designed, and this is the wheel load, and each wheel load is about 25 kilonewton, and there are 8 wheels. And this wheel is located almost 1 meter from the facing element of the wall, so which is designated at x. So x is equal to 1 meter. So we have also earlier shown that what will be the stress due to wheel 1 and 2. Now I will focus that what should be the stress due to wheel 3 and 4. Here we know that total Z in meter, this is 8 meter depth, and we are considering 0, 1, 2, 3, 4, 5, 6, 7, 8. And from this we have to calculate what is N value. N value is equal to Z by H. We know what will be the height of the wall is about 8 meter. So considering that Z is equal to 1, so N value will be 1 by H is 8 meter, so 1 by 8 is equal to 0.125. Similarly, when Z value is equal to 2, so 2 divided by 8 is 0.25. Then when Z value is equal to 3, 3 divided by 8 is equal to 0.375. When Z value is equal to 4, 4 divided by 8 is 0.5. When 5, then 5 by 8 is equal to 0.625. Similarly, 6 by 8 is equal to 0.75, 7 by 8 is equal to 0.875, and 8 by 8 is equal to 1. So we know what will be the N value. And now, what is X? X, as I mentioned, that from the facing element. So you can see here that this is the wall. Let us say if this is the wall, and this wheel that is number 1, and wheel number 2, wheel number 3, wheel number 4, 5, 6, 7 and 8. So we have shown that what will be the stress here for the wheel load 1 and 2. We have already calculated. Now here we want to show what will be the stress due to wheel 3 and the 4. So you can see that these 3 and 4, which is located from the vertical face of the retaining wall, from here to here is about 1 meter, and here to here is 0.4 meter. So this wheel load 3 and 4 is located at a distance of 1.4 meter. That means this is x is equal to 1.4 meter. So here, that's why this x is meter is shown 1.4 meter, either 3 or 4, both the wheel is located from the vertical place of the retaining wall is 1.4 meter. That's why x is equal to 1.4 meter. Now you have to calculate that m. M is equal to x by h. So x is 1.4 divided by 8, 0.175. So x is constant. So this m value also 0.175 is constant up to depth of 8 meter. Now we have to calculate the sigma h HA square by QP. Now what is sigma h HA square by QP? Now we know that earlier from this Boussinesq pressure distribution that if the m value is less than equal to 0.4, sigma h HA square by QP is equal to 0.28 n square divided by 0.16 plus n square whole to the power q, if m value less than equal to 0.5. If it is that m value greater than equal to 0.5, then equation is different, which I have explained also earlier. Now in this table, because m value, you can see m value is 0.175, so it is less than equal to 0.4. Therefore this sigma h by HA square QP is equal to 0.28 n square by 0.16 plus n square whole to the power q. So we will use this equation to calculate that what is sigma h by HA square QP, because n value is known to you. This n value is known to you. So you can calculate sigma h HA square by QP. So in this table, that's why it is putting this value of n. So you calculated that sigma h HA square by QP value. So you will have putting n value in that equation, you can have 0.81, 1.59, 1.45, 1.02, 0.66, 0.42, 0.27 and 0.18. Now what should be the sigma h for the wheel 3? So let us say that for a depth of 2 meters, and what should be the sigma h value? Now see, from this equation sigma h HA square by QP, you know what will be the value. You know this value is equal to, at a depth of 2 meter, is 1.59. That means you know sigma h HA square by QP is equal to 1.59. Now I am showing you here that we know that sigma of h HA square by Q of P is equal to, you calculate at a depth at Z is equal to 2 meter, you calculate this value is 1.59. So when at a depth of 2 meter, sigma h by HA square Q is 1.59. You substitute value n and you find it is 1.59. Now you have to calculate sigma of h. This is unknown. H is 8 and QP is point load, that is 25. That means this will have a 25. This is, this point we are determining, this is 25. So QP is 25. So 25 is known to you. So you can substitute this value of QP. QP is equal to 25, that is KPA, and H you know that what will be the height. So you can calculate that what will be the sigma h. So you can obtain the sigma h value at a depth of 2 meter is equal to 0.62. So similarly, you can calculate sigma h at the different depth. So 1 meter, 2 meter, 4 meter, 5 meter, 6, 7 and the 8 meter. So you can calculate sigma h. Now we are considering wheel 4. So here you can see that wheel 4, we are calculating location for the stress calculation at this point, and this is the wheel 4. So this wheel is the 4 which is making at an angle of 45 degree. Let us say this is theta is equal to 45 degree, and you want to measure the what will be the stress, or which you call the sigma h dash. So sigma h dash for the wheel load 4, what it will be. So when you want to calculate the sigma of h dash, you can see here for at an angle theta, here theta is equal to 45 degree, and this is the equation, that is sigma of h dash for the wheel load 4 will be equal to sigma h cos square 1.1 theta, and you know what is sigma h, you know what is theta value 45 degree. So then you can calculate what is sigma of h dash. For an example that you know at a depth of 2 meter, this sigma h value is 0.62, it is known. So sigma is 0.62. So then sigma of h dash will be 0.62 into cos square 1.1 into theta, theta is 45 degree. So you can calculate that sigma h dash at any point. So let us say that I am showing this again, this equation also here. You want to calculate sigma h dash is equal to sigma h into cos square 1.1 theta. Now you know at depth, let us say z is equal to 2 meter. So sigma of h value is known, sigma of h value is equal to 0.62, and theta you know this is making at an angle of 45 degree. So you substitute the value of sigma h and theta here. So then you can calculate sigma of h dash, and that will give at a depth of 2 meter about 262. So you can calculate that sigma h dash at a depth of 2 meter 0.6262. Similarly, you can calculate for the depth 3 meter, 4 meter, 5 meter, 6 meter, 7 meter and 8 meter like this. So this you can calculate what will be the stress for the wheel 3 and the 4. Now we will consider for the stress due to wheel 5 and 6. So you look here that 5 and 6. So this is the 5 here and this is the 6. So 5 and this is 6. So we have to calculate what will be the stress for the wheel 5 and as well as wheel 6. So location of the stress calculation at this point. So for the wheel 5, so what is the distance x? So that means what is the location of this wheel from the vertical face of the retaining wall. So we know this is 0.4, this is 1.4 meter, and then this is also 1.4 meter. So this is also 1.4 meter. So total will be x will be now 2.8 meter. So this wheel 5 and 6 are located from 2.8 meter from the vertical face of the retaining wall. So this is x. So this x is here, you can see 2.8 all along the depth. And because this is z 1 to 8, so n will be the same, and now x only will change 2.8. Now you have to calculate what is m. M is equal to x by h. You know what is x and h, because x is constant 2.8, h also constant 8 meter. So x by h is equal to 0.35 is constant all along this depth. Here again you can observe that this m value is less than equal to 0.4. Therefore, you can use this again equation sigma h h square by qp. So you can adopt this equation because this m value is less than equal to 0.4. So you can adopt sigma h h square by qp is equal to, in terms of n, 0.28 n square, 0.16 plus n square whole to the power cube. Now you know what is the n value, and so you can calculate sigma h h square by qp. So here you calculate and find that sigma h h square by qp. For at depth 2 also it is the same, because m value is always less than 0.4. So then you have to calculate again what will be the stress on wheel 5. So stress on the wheel 5, again you know sigma h h square by qp is equal to this n value is known. Let us say at a depth 2, this value is equal to 1.59. So if this value is equal to 1.59, I am writing here again. If you know sigma of h square by q of p, and at depth, that is z is equal to 2 meter, and this value is equal to 1.59. Now h is known, 8 meter height, qp also that wheel qp is also 25, so qp also is known 25, so h is known 8. So you can calculate what the sigma h for wheel 5. So for wheel 5 at a depth of 2 meter, the sigma h will be equal to 0.62. So you know what is sigma h is equal to 0.62. Now you have to calculate that what will be the stress for wheel 6. You can see here wheel 6 is located here, which is making, we have to find out that what will be the stress of the wheel for wheel 6, and which is making at an angle, let us say theta is equal to 26.6 degree. So this angle is 26.6 degree. So we know that theta angle is equal to 26.6 degree. So we know that equation to calculate the stress, that is sigma of h dash for the wheel 6, and let us say at a depth of 2 meter. So sigma h dash will be equal to sigma h in cos square 1.1 into theta. Now theta value is known 26.2 and sigma h value is known. So this is sigma h 0.62 into cos square 1.1 into theta 26.6. So sigma h at a depth of 2 meter you can calculate, and this will give 0.472. So this you calculate what will be the stress for the wheel load 2. Then this is 0.467 kilopascal, sigma h dash. So we calculated for the stress for the wheel load 5 and 6. Now we have to calculate stress due to wheel 7 and 8. Now you can see this is almost constant, and what is the location of x? So location of x, this is for wheel load, this is 7 and this is 8. So this located from here to here 2.8 and this 0.4. This is 0.4. This is 0.4. That means x will be equal to 2.8 plus 0.4. That means x will be equal to 3.2 meter. So for the wheel load 7 and 8, x is located from the vertical place of the retaining wall is about 3.2 meter. And that's why this x value 3.2 meter. That's why the x value is 3.2 meter all along the depth. But again you calculate m is equal to x by h, x is known. Here also you find that m value is almost less than equal to 0.4. Suppose if m value is equal to greater than 0.4, then we could adopt another equation which I have previously explained. But in this problem here that m value is almost 0.4. So that means we are using the same equation and to calculate what is sigma h by h square by qp. You can see for the depth 2, again this value is the same 1.59, and for the wheel load 7, so you calculate the stress, this is 0.62, and similarly because here wheel load 8 and which is making at an angle 23.6 degree. So you know what is the theta angle, 23.6 degree. So let us say I am just showing you for the wheel load 8 only. Wheel 8 at depth this is equal to 2 meter, and you know what will be the sigma h dash. This is equal to sigma of h into cos square 1.1 theta, and theta is given 23.6 degree, and sigma h at a depth of 2 meter is 0.62. So you can calculate sigma of h dash is 0.62 into cos square 1.1 and theta is 23.6. So you can have at a depth of 2 for the wheel load 8 will be equal to 0.472. So this you can obtain 0.472. So you can calculate for any other depth what will be the stress. So here we calculate what will be the stress for the wheel 7 as well as for wheel 8. So we completed the stress for the wheel load 1, 2, 3, 4, 5, 6, 7 and 8. So here you can see that variation of the stresses here, and this is the depth. At any depth you calculate what will be the total stress. So you know what is sigma h, you know what is sigma h of dash. So, you know that what is the wheel from this table, wheel 7 and any depth, wheel 7 and wheel 8. So, you can calculate what is sigma h and sigma h dash. Similarly, for wheel 5 and 6 at depth 2, let us say what is sigma h and sigma h dash. Similarly, for wheel 3, you can calculate what is sigma h and sigma h dash, and we have also earlier calculated what is for the wheel 1 and for the wheel 1 and 2, we have already calculated, and at a depth 3.62 and 0.262. So, this is almost 4 times of 0.62 and 4 times of 2.62 at a depth 2, and if you calculate, you can obtain at a depth 2 about 3.844. That is summation of sigma h and sigma h dash at depth of 2 meter. So, what will be the stresses, horizontal stresses is acting on the wall. So, for various depth, so 3 meter, you can sum up the sigma h plus sigma h dash, which will give 3.507. Similarly, for 4, when z is equal to 4, this summation will be 2.457, 5 1.585, 6 1.010, 7 0.654, and at depth 8 this will give 0.434. So, we can see that with respect to the depth, this stresses, horizontal stresses, it is initially it is increasing and it reaches to some maximum value, and then you can see that this value is decreasing. So, now on the right hand side, we can plot a relationship between that what should be the stress and what should be the depth. So, this is the depth and this is the what will be the lateral stress. So, you can substitute for the different values of z and corresponding the stress. So, you can have 1 meter, let us say 1.954, then for 2 meter, which will give almost the maximum value 3.844, and then for 3 meter you are having 3.507, 4 meter you can having 2.457, 5 meter you can have 1.585, and 6 meter you can have 1.01, 7 meter 0.654 and 0.44. You can see it is increasing and it reaches to the maximum value and then it is decreasing. That means it can be observed that after this depth 2 meter, their lateral horizontal stress will be the maximum. So, these maximum lateral horizontal forces pressure are to be considered into the design for the wheel load. So, this has to be added with the reinforced soil retaining wall and to calculate. Suppose if you do not consider, then there is a possibility for the bulging. So, we talk about that what should be the pressure due to the wheel load and at what depth you can reach to the maximum value, and then how it is decreasing. So, you can have some idea about the lateral pressure due to the wheel load. Now, we will discuss some design critiques. Sometimes the reinforced soil retaining wall structure collapse due to development of excessive hydrostatic poor water pressure and lack of proper drainage material in front, beneath and behind the reinforced soil zone. So, it is necessary to prevent the water from entering into the reinforced soil zone from the top. Therefore, a layer of geosynthetic clay liner or geomembrane are to be placed at the top as a waterproof material. Apart from that, to prevent the excess pore water pressure, you need proper kind of the drainage system. You should provide sufficient that permeability of the material, and at the same time you require adequate transmittivity, which can fulfill the criteria for the proper kind of the drainage. You can provide even then with the geocomposite material, geonet or geotextile material at the back of the retaining wall for proper drainage. Now, here is a one schematic view or segmental reinforced soil retaining wall with proper drainage system. So, this is the wall, this is the number of the layer of the reinforcement, that is geogrid material, and a back here providing with the proper kind of geocomposite drainage, and this is the reinforced field back whose unit weight is gamma b and angle of internal friction pi b and cohesion is Cb. This is the foundation soil which is designated unit weight of foundation is gamma f, angle of internal friction of the soil is pi f, and this cohesion value is C of f. And this is the reinforced field whose angle of friction for reinforced zone is gamma r, angle of internal friction of reinforced soil zone is pi r, unit weight of soil in the reinforced zone is gamma r. And you are providing with the drainage material at the back of the retaining wall. You can provide geotextile, geocomposite or the aggregate, and also at the top you are providing with the geomembrane material. So, water cannot percolate from road to this. So, you are providing with some design of the pavement here, where you are in 200 GSB or 150 WMM or 130 dBm or 50 BCC, or you can provide with the geotextile material to reduce the thickness of the pavement. And this is the frictional slab, and this is the anti-crash barrier to prevent any accident. So, you should provide the anti-crash barrier, and this also you require for the design, and this is the coping. Here is the coping. And when you construct the wall, always you have to provide the wall barrier, that is precast concrete segmental. This is facing panel, and you can use M35 of concrete grade, and also back you should provide with the minimum of 1200 millimeter, and you can make a slope, and this is from this leveling part, it should be about 600 millimeter, and this also I have discussed earlier. This is about 600 millimeter, this is 200 millimeter, that is the leveling plat, and for M15 that concrete grade you can use it. So, here is the HD, this is the design in length, and this is HF from here to the before the coping here, and this is HF here considering from the road. This height is about H of M, and this near to the coping from this height is about H of F. Next, I will show that Excel program for mechanically stabilized reinforced soil wall. So, this is the figure which I have also little bit shown you. So, this is the wall design height from here to here is about 8.356 meter, and this is the wall height, that means facing length is about 8.90 meter, and this is mechanical height, that is 9.747 meter. So, I talk about all this parameter here, and then we use that mechanically stabilized earth wall reinforced soil slope for reinforced soil. This is US transport FHWA, and apart from that we have also used that BS code that is 1995, that is reinforced soil wall that we have shown. So, we will follow this, these are the code, this code will follow it. Okay, then I will show you that what should be the design input for this. So, this is the input soil parameter, and this is the reinforced infill soil, there is C, and the retained soil and foundation soil. This C value we considering is 0, and for the pi value is for reinforced infill soil is 35 degree, and retained soil 35 degree, and foundation soil 30 degree. I have already explained that what is the reinforced soil fill and what is the retained soil and also foundation soil. And gamma unit weight of the reinforced fill is 20 kilonewton per meter cube, and the retained soil is 20 kilonewton per meter cube, and the unit weight of foundation soil gamma is 18 kilonewton per meter cube. Then what will be the input wall geometry? So, input wall geometry, this design height I have shown that is 8.356 meter, and wall height is 8.9 meter, and average unit weight of the pavement is 22 kilonewton per meter cube, and HF minus HD will be equal to 0.544 meter, and this H of pavement is 1.391 meter. Now, input interface data. So, interface friction angle between the retained soil and infill soil is 0. Coefficient of interaction relating to the soil reinforcement bond angle with tan phi is equal to 1. Coefficient of adhesion retained to the soil cohesion to soil reinforcement bond is 1. Now, also you have to put input external load. So, design load surcharge is 30.6 kilonewton per meter square, live load surcharge is 22 kilonewton per meter square, vertical strip load is 15 kilonewton per meter square and horizontal strip load is 0. Now, input strip load, that is here given in detail. Distance from the wall edge to center of the strip load is 0.9 meter and width of the strip load is 1.8 meter. I am showing you that, so it is like this. And this is B, this is B, and this B is 1.8 meter, and this is the wall. Okay, let us consider this is the wall, and this is dispersed with this slope horizontal to vertical is 1:2, and similarly this is also 2 vertical, 1 horizontal. So, any strip where is the vertical stress is acting, this is sigma of B, and this the center line, and where that strip load SL is acting, and from this center line to here this distance is equal to, that is D, and this D is equal to 0.9 meter. So, where it has shown distance from the wall edge to the center of the wall edge to the center of the strip footing is equal to 0.9 meter, and width of the strip load, this is width of the strip load, that is B, is equal to 1.8 meter. So, this is how the disperse of vertical strip load through the reinforced soil. This is a kind of back wedge method analysis. Now, apart from that, you have to add that what will be the input soil geogrid interaction parameter. So, coefficient of interaction for pull out is 0.85, coefficient of interaction for direct sliding equal to 0.85. Now, input seismic parameter. So, design horizontal seismic coefficient, that is AH, is equal to 0.18, and input facing detail, that means thickness of the facing panel, that is 0.185 meter, and unit weight of the facing panel is 25 kilonewton per meter cube, and depth of the groundwater table below the ground level is about 10 meter. So, these are the parameter you have to take as a input soil parameter. Now, we will calculate the external stability of the wall. For external stability, first is the static loading. We know design height is equal to 8.36, mechanical height is equal to 9.75, and tall length of the reinforcement 6.825, or you consider at about 6.9, and embedment length is 0.8, and coefficient of active earth pressure is equal to 0.271. Now, what is total horizontal earth pressure force per meter run, RH. You have to calculate what will be the total horizontal earth pressure force. The due to soil pressure, this is 283.8294 kilonewton. So you can calculate this pressure, that is, you know what is K of A value, that means K of A value is known, you know the gamma value, and you know the what will be the height. So you can calculate half K gamma H square. And there are combined load, this is A, and combined load, this is B. So combined load A, when it is the maximum value, when all load are taken into consideration into the design. This design has been made as per the BT Standard Institute 1995, and this also combined load for the B, where it is due to the overturning load. So for the due to soil pressure, you have calculated for A this value, for B also this value, due to the del load. So this is when it is the del load, that means you know what is Ka, and you know what will be the Qd value, and also you know the H value. Also you have to consider that some factor of safety. This factor of safety for the A and the B, for the various soil pressure, del load or the live load. So this is given in the BS code specification. So for this factor of safety is equal to 1.5, and for due to also soil pressure, this factor of safety 1.5. So when you do for the soil pressure A, so what is half Ka gamma H square into 1.5, you have to multiply. Similarly for soil B, 1.5. Sometimes this give also the different factor of safety value for the combined load A as well as combined load B. Similarly for the del load, you can have 103.9394, and for B 103.9394. And due to the live load, this is 74.727. That is, live load is K into Q into H, and also you have to multiply that factor of safety for A 1.5, similarly for B also 1.5. And due to the horizontal steep load, this is 0, 0. So you can calculate what will be the total horizontal earth pressure force per meter run. So you can, RH is total for A 462.4966, and for B total horizontal earth pressure force per meter run, RH is equal to 462.4966. Now next we will discuss resultant vertical force per meter run, and RV. That also for combined load A and combined load B. Now due to the weight of the field for A, so you can calculate that what will be the weight of the field. You know that a reinforced soil wall which has a height capital H, L is equal to length of the reinforcement, and gamma is equal to unit weight of the reinforced soil. So weight will be equal to gamma into H into L. So you know what is the gamma for the reinforced soil zone, you know what will be the height of the wall is given, you know what will be the length of the reinforcement. So you can calculate that what will be the weight of the field, and at the same time, as for combined load A, what will be the factor of safety. So factor of safety is 1.5. So you have to multiply that gamma into H into L into factor of safety 1.5. So you can obtain 1729.692. Similarly, for the combined load B, you can calculate, you can have 1153.128. So there may be variation of the factor of safety as per BS code specification. So due to the surcharge load, you can also calculate that what will be the combined load A, that is equal to, you know that what will be the L, you know the what will be the del load QD, you know the what will be the surcharge load plus QL into that factor of safety 1.5. So this will give 22.5, sometimes this will give 1, then this will give B, it will give 15, and due to the inclined soil pressure, this is 0 and this 0. So resultant vertical pressure, you can have RV is equal to 2296.602 and for RV 1379.268 kilonewton. Now you calculate the disturbing moment MD. So you know that, so we calculate the resultant RV pressure and we calculated the R of B. So disturbing moment MD is equal to 1537.031 for A and for B 1537.031 and resulting moment MR is 7865.902, this is all kilonewton meter, and 4720.225 kilonewton per meter for B. Now check for the sliding, that is long term drainage condition. So you required factor of safety is 1.20 as per BS 8006 1995. So partial factor of safety is equal to 2.865187. If it is, then it is safe, and for case of B it is 1.720743, means it is safe. Check for the bearing and tilt. This is a long term drainage condition. So you require factor of safety is 1.35 as per BS 8006 1995. Now as per Mayer distribution, you can calculate the eccentricity, and that is 0.69246 meter for A and 1.4114 meter for B. So effective width of the foundation, this is 5.511509 and for B 4.615773. You know what is the effective width L minus 2 of E. Factored bearing capacity pressure in case A it is 416.6921, this kilonewton per meter square, and for B 298.8163 kilonewton per meter square. Now you know that what is bearing capacity factor, NC value 30.14, N gamma 22.4, NQ 18.4, and water table correction factor is equal to 1 for A, and similarly for B this is eccentricity 1.1421, sorry, NC factor will be 30.14, N gamma is 22.4 and N of Q is 18.4 and the water table correction factor is 1. So you can calculate what will be the ultimate bearing capacity, that is 1361.68 kilonewton per meter square for A and 1181.1 kilonewton per meter square for B. So you can check that what will be the partial factor of safety, that is for A 3.384805, so it is safe, and for B it is 4.152715, so it is the shape. So you know what will be the factor of safety for A and B. So it satisfies this criteria, bearing capacity criteria, it satisfies the overturning moment criteria. So it is the safe design. So here we are telling reinforcement tension for load case A. Here is the Zi is the depth from the top of the soil, that is 0.2, then 0.8 and 0.6, 1.4, like this, it goes up to 8 meter. Now this is H of J, that is equal to, you know, the H minus this Zj. So H minus Zj, it will give 8.16. So this is the SVJ, that is spacing between the two reinforcement. So here it is 0.5, and then we are keeping constant the spacing about 0.6, and at Z8 is 0.656. So almost we are keeping the spacing constant, almost 0.6 meter. Here MDJ, what is the driving moment, you can calculate for various depth. So you will obtain this defined value, and driving moment value is, you can see gradually it is the decreasing. Then it is the E of J, that is the eccentricity of resultant vertical load at the jth level in the wall. So you can calculate what is the eccentricity for varying depth. And D of I in meter, that is a function of Hj, B and D. I have already explained what is Hj, and the B also T for the footing, and D, so you can calculate Dj at various depth. And here is the Tpj, that is tensile force per meter run. This is the tensile force per meter run. Then Tsj, that is the tensile force due to the vertical load. So this what you can calculate. And next is Tfj, that is Tfj is the shear force developed due to the horizontal shear. So shear force due to horizontal shear is 0 here. And then is the Tcj, and that is the tension due to cohesion, and which we consider as a 0. So you can calculate what is Tj, that means tensile force, that is total tensile force. So you can calculate the total tensile force. So for the load case A, so total tensile force at different depth you can calculate. So this is 64.54, 60.15, and then 55.25, 50.67, 46.39, 42.36, 38.55, 34.94, 31.51, 28.23, 26.09, 22.08, and 19.2 and 17.99. You can see that how the forces are decreasing, reinforcement tension force is decreasing. So this is table shown the reinforcement tension for load case A. Similarly, you can check that what will be the rupture of the reinforcement. So required factor of safety for the rupture of reinforcement is 1.1. This as per BS 8006 1995. The same, this is the depth, this Hj is the same, and this is the spacing is the same, and you can calculate here. You have been shown for case A and the case B. This is Tj and Tj. So you can calculate Tj for this for different depth. Similarly, for case B, it has been calculated and shown here. Then what should be the reinforcement property? Then ultimately, you can have the tensile strength, ultimate tensile strength of geogrid material 150, 150, then 120, 100, 80 and the 60. So you can distribute the strength, and then you can find out the reinforcement property, and you can see you can calculate what will be the factors. This is 2.113, can have 2.113, and what will be the design tensile strength. So you can calculate that what will be the factor of safety. You know, this is the design strength value, and then for case A and B, yes, this is for PSF, that is provided factor of safety for case A. So this will be, you have calculated what will be the T of D for the design is known, and Tj what is the requirement. So provided factor of safety for case A will be equal to the Td design divided by Tj required. So if you divide this, then you can have 1.30. So like this for case A, you can calculate what should be the provided factor of safety. Similarly, for the case B, you know what will be the Td design, you know what will Tj require, and then you can find out what will be the factor, provided factor of safety for case B. So this way you can calculate, and you can see as for the code specification it is 1.1. So it is satisfying all the criteria either in the case of A or in the case of B. So this is the part that which I showed you, that what will be the check for the rupture of the reinforcement, what will be the required factor of safety. So it is the safe. So for any length or any height, so you can design with this Excel program. With this I finish this today's lecture. Any question? Thank you for listening.